All right, so it's an immense pleasure to introduce the one, the only, the monodromima Herbert Clemens.
And thanks for the invitation to come back. And, this is going to be, there will be no new mathematics in this talk. There is a problem, and the problem is a communications problem, which I think many in the two fields have experienced over the last 20 years between string theorists on one side and algebraic geometers on the other side, because it's two languages and it's a fair sized ticket price to learn the second language. So my physics collaborator and I are actually, well, besides the fact that we're both retired and old and think very, very slowly, I don't know physics, and he doesn't know the algebraic geometry, and we haven't been able to attract enough attention to the connection that we think we have made. So this is an effort for me to give you algebraic geometers a kind of little seminar in what the issues are. And from my perspective, what we are using is so classical algebraic geometry that the younger people in this room, at least when I was here and gave a preliminary talk last year, didn't know the math. I asked what a Cayley octad was, and about one hand in the room went up. So Cayley octad comes from 19th century, absolutely beginning classical algebraic geometry. I'll say it before I start, and I even mentioned it in the talk. If you ever, maybe even a little bit because of this talk, want to learn any of this stuff, Igor Dolgachev has made a tremendous contribution to the discipline by talking about those classical things over the years, putting together a book, Cambridge University Press, called Classical Algebraic Geometry. And everything except one thing that we are applying is in that book. The other thing that will be central to what we do and get us from the visible universe over to the twin universe, that's dark matter, dark energy, and all of that, will be in another Dolgachev, Kosek, Dolgachev, Enriques Surfaces 1, which you can find on his website.
I was hoping you'll say 2, but I guess I won't see that. I won't see it.
So they are, our method of passage is from a very special Enriques surfaces, which is the, so pair Enriques surface polarization, okay, Neff and Big divisor has the families, like for K3 surfaces, have a numerical classification, be positive integers. And those with positive integer one of the subfamilies, and that's why it's in Enriques surfaces one also, is the one that we use. That's the one where the linear series associated to the polarization has fixed points. And I mean, it's a primitive class and it has fixed points. If an Enriques surface polarized has fixed points, it has exactly 2 fixed points. And what we're going through is how you do Yukawa couplings, that those 2 fixed points, one in the visible sector that we experience, and the other in the twin sector. And there's a divisor linking line bundles on those 2 fixed points that we think is really fun, but we have not been able to attract any attention to it. So if you ever talk to string theorists, please remember us. Okay, that's the introduction. All right. So, and there's no, the end of this talk will be before or when that, you have a little ding thing that rings after an hour, right? Or after 45 minutes.
I don't, but I remember where we start.
Anyway, well, somebody put up your hand and told me to stop, and that's when we'll stop. So I've got tons of slides, and I'll go in the direction that any of you ask a question about it. So here we go. Okay. So this is the written version of what I just said. So I think we can go on from that. So we have Calabi-Yau family. We're interested in Calabi-Yau family, or actually a Calabi-Yau threefold in Calabi-Yau family of threefolds. That's called heterotic theory. And how to pass between that and Calabi-Yau fourfold, that's called F theory. When you do your physics and cycle theory and all that in the fourfolds. And we also have, besides the elliptic structure on all of those, we have a second section. So more domain group, right one. And this we may get to, this business about the Euler characteristics divisible by 24. But I won't go there at the beginning. Okay. So yeah, the other thing is I have old man's tremor. That's why it's my that's why I've been doing it this way. Because last year I was shaking fingers and it would go backwards and things like that. So we'll take Z2 quotients of an elliptic K3 surface, which is the surface measuring the discriminant locus of the families of cubic curves that the threefold Calabi-Yau and the fourfold Calabi-Yau are satisfied. So it'll be an elliptic curve for the threefold, that heterotic side, and it'll be a K3 surface that sits over the final geometry, well, we'll still have an elliptic curve on the on the heterotic side, but we'll have that Enriques, a very special Enriques surface on the F theory side. Okay. So let's just zoom through what we can here. And what we're going to talk about first is let's skip all that. In the beginning, there was, I feel biblical every time I say this. In the beginning, when the whole universe was just a dot or God knows what. Well, maybe it was. I won't go there. Anyway, there were two E8 symmetries, complete symmetries out there. And what the physics people, the string theorists are interested in is, I always think to myself, the first 30 seconds after the Big Bang. But anyway, so energy was concentrated and incredibly high, 10 to the, you can't imagine how many zeros, okay, GeV. And then it starts spreading out. And that's what's going to, as it spreads out and symmetry breaks, that's where matter and energy are created, basically. That's I mean, if anybody knows all the physics correctly, because this is just my what I learned from my Anyway, so one of the things that we really like about that we worked out was, as we began doing the physical model, using something from number theory called the Tate form, that we'll do first. We were forced, as we tried to do the steps that my colleague told me to do, we were forced to actually incorporate both E8. And and it leads to something that's my aim, to get through early enough that it won't miss it. That deposits one Yukawa coupling, which is where energy and matter are created, extinguished. Anyway, where you pass from two groups of symmetry over curves to where they intersect, at which time symmetry increases to basically the smallest subgroup of E8 that incorporates both of those, for which those two groups of symmetry are a subgroup of. So symmetry goes up as these couplings occur. So, and basically people study symmetry breaking of visible E8 to SU5 cross SU5 divided by Z5 second group. And that symmetry, the SU5 gauge, is the one that then, by something called the Wilson line that we'll also talk about, gets broken to SU3 cross SU2 cross U1. SU3 is the symmetry of the strong force that holds protons together. SU2 is the weak force that holds electrons in orbit around protons, and U1, the U1 group is electromagnetism, which has a circle group of symmetry. And then the conceptual framework is those are three of the four basic forces. The fourth basic force is gravity. And at the beginning, all of those four forces were essentially fit together. And somehow there was something twiddled something, and gravity spread out hugely, and the other three basic forces stayed subatomic. And it's the model of that process through the representation theory of the various groups. That's what string theory very roughly explained. Okay, so you have that. And Yukawa couplings, like I just said, increased symmetry in between SU5 gauge in particular and the E8 in the visible sector. And basically they say, we don't know anything about what happens to that E8, or at least very few have studied. There's beginning to be a surge in research on dark matter and dark energy from this point of view, but it's in its infancy. Okay, so the mathematical tool for all of this came from number theory. And it's an algorithm of John Tate, and I'm looking 1975. So this is also very, very classical. And basically, it's looking at cubic curves over the interface, and at where, if you will, bad primes occur, and what happens. So if you do it just by high school algebra, and you write this. This is a family of cubics in WXY, which we'll use forever in this talk. WXY coordinates is a family of cubics where the coefficients are arranged so the discriminant of the family of cubic curves, okay, is given by the divisor, the polarizing divisor, so that'll be d to the fifth power. You have an in the Kodaira, well, I'll go on to it. In the Kodaira classification, oh, sorry, so I said it wrong. The 12th power, the fiber is I5 fiber. The cubic fiber in the Kodaira classification is an I5 fiber when the discriminant has is degree 12. That's going to be a rational cubic family, let's say over P1. Okay. And basically, it doesn't matter the dimension if the divisor is the anti-canonical divisor of the base, then the Calabi-Yau n-fold, the n-fold is Calabi-Yau. The elliptic structure, and there's our sort of tautological second section. And all the action is taking place over that reduced discriminant. And it will be a K3, and then we'll take a N2 quotient, and we'll have this in Greek weights. Any questions or comments, or did I say something stupid, which I may have this one? Okay. So that's an easy section to get. Remember the coefficients I was denoting by A, and they went from A naught, skipped A1, and then A2 up to A5. And then there was a Z that was multiplied by a Z. And that Z is equal, or it's equal to 0. That's indicating the discriminant component of degree 12. Anyway, so I just put in here, and we'll just zoom through it. It's high school algebra to put this thing into Weierstrass form. And so I won't linger there unless there are questions. Just is what it is. The Z will sometimes have a hat and sometimes not, that I'll use some for some purposes, but basically we're referring to what the physicists call S-gut, which is that place where the cubic curve, well, in the SU5 locus that we were just talking about, the Crepit resolution is a string of 5 sausages, just 5 rational curves making up a circle. That's the extended Lincoln diagram of SU5. So something else that will be central to this is deformation theory, and that's the only connection with the honoree of this conference. Okay. And it's deformation theory of singularities, not of complex setup. So, okay. So the point of view is you start with the cusp, singularity, and you deform by increasing the AJs from 0, but leaving the Z, which is that thing, giving the discriminant untouched. Okay. Okay. All right. So cusp parameter, and then there's something called the spectral variety that the physicists use all the time, and it's spectral like line bundles and spectral presentation. what's going on here. You form it by taking the perturbation of the cusp into some of these A directions that we'll sort out in a minute. And then you take the derivative at zero, basically, and the parameterization of the cusp was, t squared t cubed. So this thing, you substitute that parameterization into the Tate form, and well, it kills the cusp, but gives you a way of finding in the singular fiber of the family of cusps. Now I'm going to skip that for a moment. So it gives you a way of finding the nature of the crepant resolution of the singular total space of the Calabi-Yau threefold or fourfold. Okay, because that's going to be the place we're going. So there's our Calabi-Yau threefold, fourfold, fivefold, sixfold. Doesn't matter as long as the where D is the anti-canonical bundle of B. And S is that S gut that we're going toward. And the general fiber, as I mentioned, will be I5 fiber over S gut. But there will be sub-varieties inside of that S gut where symmetry will increase. And that's what we're looking to be able to parameterize. So, and it's the crepant resolution that we're looking for, because got to keep Calabi-Yau. So now there is one canonical crepant resolution that David Morrison taught me this when we were starting to learn about this stuff. And this is now just miraculous. There is the versal deformation of the E8 rational double point singularity. Those are free parameters. They have weight, and our Chandra theorem, that versal deformation is the complexified carton of E8 divided by the Weyl group. Just a fraction. Okay. And it's a it's a deformation, it's weighted deformation space, quotient singularities. And again, I'm going to just skip through that. That's our deformation space, the versal deformation space of E8. Versal deformation. And the Priest-Gordon-Grothendieck is that if we pull the family, the versal deformation of the E8 singularities back from parameter space being the complexified Cartan divided by the Weil group to the complexified Cartan. And all of this basically is in a formal or small neighborhood of zero in that deformation space. That there is a God-given canonical crepit resolution of that family. So the total space of that family given by looking at basically, well, I'll just say the words, Borel subgroup at semi-regular. Robert, you're nodding. That's the little P1s that get put in, yeah, are created by the array of Borel subgroups. Yeah. And right. So now this is a totally open question that I will put before you. Okay, let's rescale the Tate form. So the rescaling basically is by setting the A naught equal to 1, if you will, or dividing through by weighted A naught. So, I mean, if you caught where the bundle of projected spaces that the Tate form is defined on, you'll see that the A's are in O of D, the Z's are in O of D, W is in just the structure group, X is in D squared, and Y is in D cubed. It's this weighted space of weighted quotient singularities deformation. Okay, so when you put it in that form, and you take that this Z that's defining the multiplicity 5 component of the discriminant locus, and after you've renormalized, you turn the Z into a fiber coordinate, okay, rather than a base coordinate, just formally, and you write down what you have. You have a family weighted homogeneous rational double point variation, just like that, fits into the full semi-universal deformation of the E8 singularity. And basically, what the Tate form is giving you is a hierarchy of symmetries. So if you make all the A's equal to 0, that's obviously just the cusp. It's also not semi-stable. but anyway, if you take A naught non-zero, then what you have, and you divide through the A's by E naught, well, I guess I should go back. Oops. Yeah, you divide all the A's, that CJ rather than AJ, that C is for Casimir. And then theirs are weighted homogeneous and given by the Tate form. So basically, as these things grow, and we'll see exactly how they grow in just a second, as these things grow, the rational double point singularity goes just alphabetically down from SU5, that is A4, through the exceptional groups. And this is what I called you about a year ago. Okay, how do you get from the cusp to E8? Well, basically, here is the cusp. When you put W cubed instead of that Z to the fifth, or as a W cubed as the variable in the WXY plane, you get a pencil that starts at the cusp singularity, has no other singularities until it gets to the other end of the pencil, that is the W cubed. You resolve that and you get the Dinkin diagram of extended Dinkin diagram of E8. Did I get it right?
Yes, although there's a long
Huh?
there's a long backstory behind that also. But
in 30 seconds or 20
well, I mean,
minutes.
I mean, there's this sort of rich literature of the rational double points and the simple elliptic singularities, and in some sense, I think what you're talking about is what Pinkham did in terms of the Brody-Decrease corner conjecture, that you solve it not by using the subregular elements in the Lie algebra, but you look at Del Pezzo surfaces with a cusp singularity as a hyperplane section. And then keeping that gives you the unfolding of depending what the Del Pezzo was, gives you the unfolding of the E6, E7, or E8 singularity. And then there's another point of view in this other series of papers John and I wrote too. But, kind of a long story.
So what we will be talking about is curves inside of this S gut that have those different singular. So over them, we have the fiber has symmetries just of that hierarchy you mentioned, and they will come together at at both of the 2 points that I mentioned on the Del Pezzo, one in the visible sector and one in the twin sector, and they will come and visit at the E8 end of that pencil. So that's the picture, and yeah, I could stop now because that's what we're just going to look at that. Okay, well, I should. Okay, questions, comments. So there's the versal, and there's the one coming from the Tate form with those C's grouped so as to say, how does this thing from the Tate form fit inside of the versal deformation of the E8 singularity? And there is a totally, I mean, first of all, I mean, nobody seems to use this business about putting the Z. I mean, this is a formal change, but it always works this way. I mean, what's happening is there's the Z is the normal, the Z that is defining S gut, the singular locus of a family of cubics. It's normal. It's measuring the normal vectors to S gut. And basically what that switch is taking the neighborhood of Z inside of there and pushing it into the fiber to create the singularity. But I mean, this calls out for something that I don't think people think about, which is at the bottom line here. So the spectral variety, as I said, was detecting essentially the singular points in the fiber of the Crepit resolution of or a Crepit resolution of this thing. That's what the spectral divisor is doing. So it essentially, there is a mapping of that spectral divisor into this quotient of the Cartan divided by the Weil group. Now, if there was a way of lifting that map, then there would be a canonical family, Crepit resolution family. I mean, the spectral divisor that the physicists use all the time is just calling out to be to do that. But I mean, I know zilch representation theory, but someone who knows the algebraic geometry and the representation should figure how to do that. It's got to be there. I mean, the Brice-Grothendieck thing is so beautiful and so central and so natural for the representation theory that there's got to be a way to use that for the Crepit resolution of the Tate form. And all of this is totally general. I mean, it's not threefold, fourfold. It's in all dimensions. Okay, so let's just keep going. So why is the spectral divisor where you should look, especially in the case of heterotic theory? That is, it's a Calabi-Yau threefold, and F theory, it's a Calabi-Yau fourfold, because of a classical, well, he just called it a proposition, and it's the basic fact about if you have Weierstrass vibration, so we have the Tate vibration, right? But we changed it to the Weierstrass. First of all, the 0.001, the base section is never singular. If the total space is singular, then y has to be 0. If you have a singularity where the x is also 0 in the fiber, that's if and only if the G4 and G6 in the Weierstrass are 0, and we're at a singular point. That's a mistake. That should say the discriminant is also singular at that point. Yeah, I was messing around with these slides up till morning, and I just missed that misprint. So that in the veranda setup, that thing should be z equals 0. Okay. So that says if B is a smooth surface by the above and simple arithmetic, the only singularities in the total space will occur when both x and y are 0. So y over x is undetermined. Y over x is t in the spectral variety. So the spectral variety is the first step in unwinding the singularity. Okay. Okay, so now here comes the sales pitch for which B we should we're asking folks to look at. And then from yeah, Bill Susan. It's this that's coming. We were walking to lunch, and Bill was saying that, well, I was working on these cubic plane curves. And it's a very special family and flows, flows, and I started asking him, and it's the family we're going to put up here, canonically embedded. Okay, so our B2, our base surface, okay, is degree 2 del Pezzo. Everybody knows this, yes? Double cover of P2 branched along the corner. How many of you have never seen that? Okay. But this is, and Igor Dolbachev told me, this is the most studied family of plane quartics since the 19th century, because all the superstars are in there. Well, the Fermat, obviously, when the A is the alpha is 0, when the alpha is 1 plus I times the square root of 7 over 4. That's the Klein curve in the sky. I mean, it's usually on a different presentation. Most symmetries, 128 group of symmetries. And then there's another one that I'll mention in a little bit, which is also very special. And it's when the alpha is 34 over 25. Anyway, so the physicists like Z4 actions, Z4 symmetries. There are very few delpezos of degree 2 that have Z4 symmetries, and this is one of the families. So, and it turns out that for this passage between the visible universe and the twin universe, that Z4 symmetry is going to play a very important role. And the physicists like it because it prevents, if I can say it right, dimension 5 proton decay. So the reason that we all exist and are sitting here is because of that Z4, according to the string theory. Okay, so simply what we're going to do is make the simplest possible model that you could ever think of that has, yeah, the circuit board for this model is not going to be B2. The circuit board for this model is going to be its canonic, the variables in its canonical image in P2, namely, I'm going to use always T1, T2, T3. Is it okay? I don't put on dimensions, projective space, because we have so many of them floating around. I'll just put the variables in. And so this is the B2 is, of course, a hypersurface in the weighted projective space, because this has weight 2, all of those have weight 1. Okay, and whoops, sorry. And I mean, I picked, well, I picked to do that Z4. There are 3 choices of a Z4 according to whether you fix the T3 axis, the T2 axis, or the T1 axis. I will choose to do the symmetry, as we'll see in a minute, given by a rotation around the T3 axis. And then so that we can incorporate that in all the algebraic, I mean, 19th century algebraic geometry we're going to do in a minute. We are going to slowly change to, instead of T1, T2, T3, we're going to take the eigen coordinates for that Z4 action, which are pretty simple. But there they are. Just we're gonna rotate in opposite directions simultaneously. Once in the visible sector and once in the twin sector. Okay. So questions here. Is this okay? So then the equations for these matter curves and Higgs curve that go into this augmentation and symmetry that I was talking about before, they're going to be defined in terms of these eigencoordinates. So there will be a Z4 action on them as well. So this is just on a slide what I just said, that to look at that canonical image in P2 as the thing that is pulling all the strings on coverings, everything, all these curves are going to be given by even rational curves in hyperelliptic curves in B2 over simple rational curves in P2 here, this P2. And so we will use that. This is the branch locus. Okay. This is the plane Quartic that we wrote, and this is that same thing in eigencoordinates. And as I mentioned before, we needed a Z2 action because we don't want the K3 surface. We want for the second half of the symmetry breaking from SU5 to what the physicists call the standard model, that is SU3 cross SU2 cross U1, you need something called a Wilson line. For a Wilson line, you need a fundamental group of Z2 on your base. So where we're going for our final model will be this quotient. Basically, it's created by this would use over and over again. If you have double branch cover, another double branch cover, and you take the fibered product, that's 4-to-1 over the base. Those 4s split up naturally into 2-2 partitions or not. That is, you get an involution whose fixed point set is the intersection of the branch loci of the two entries in the fiber product. So, for instance, if you want to make an unbranched double cover of a hyperelliptic curve, what you do is you simply partition, take an even partition of the set of branch points and take the fiber product of those two hyperelliptic curves, and you have this exact same construction. But there, the curve in the middle is an unbranched. So just like here, in fact, better than here because we're not in dimension 3, this B2 hat to B2 will have only 4 isolated branch points. And our Calabi-Yau threefold will have the logarithmic business over those branch points. So our actual Calabi-Yau threefold will be smooth. Okay. Questions on that? That was probably a little easy. Let's talk about the symmetry group. Why this is so great. And if I just get in the next 13 minutes to the virtues of the symmetry group and no further, I'll be happy because it's so beautiful and it's so old that, yeah, it's old and lovable. Anyway, Dolgochev's book is tremendous. Okay, so there's Q. Think of the T1, T2, T3 axes. Yeah, so that inside regular octahedron, its barycenter is 0. And the T1 axis is coming out through this red-blue point right there. Can you see the little, where my little hand is pointing, right? And the teeth, what did I do? I'll go back. And the T3 axis is the vertical axis. Okay. So it's stationary, right-hand rule 90 degrees in the visible sector, left-hand rule 90 degrees in the twin sector. Okay, that's how the Z4 action is going to operate. Okay. So the symmetry group of that family of delpensos is exactly the full symmetry group of this cube, including reflection through the center. Okay. So the symmetry group is SU4, permutation group on 4 elements, cross permutation group on 2 elements, or it's the plus minus matrix permutation group on 3 axes. All the same thing. The S4 is fully faithful on the central the 4 central diagonals of the cube. How many of you have run across that in your mathematical life? What? Okay. Anyway, that's just gorgeous. Okay. So, and our 1 parameter family, like I said, contains all the all-stars of canonically embedded G3 curves. Okay. So this I'm gonna, so there it is in matrix form. Yeah, this is the book you want if you ever like this stuff. It is fantastic. So let's talk about roots. Where are roots? So if you know representation theory, and or if you look at Dolgochev's book, you find the E7 roots, not E8 roots, but you find the E7 roots as simply the integral cycles in the kernel of the projection to our circuit board square minus 2, self-intersection minus 2. So that's the E7 roots. And I get so excited when I talk about this book because this is like the Brie-Score-Grote thing. As you come to that, I said, God, I never do that. I looked at the cubic surface and all those 28 lines and everything, and I understood that that had something to do with E6. But I never knew the analogous story for E7. and it's just gorgeous. Maybe if I only get to this, I'll stop it because I got through even a third of one of the slides, but I don't want to go past 5:30. So anyway, you take any even theta characteristic of our plane cubic curve, and you tensor it with the canonical, with O of 1 basically coming from P2, and you take its linear series and you put it in, it maps to P3 in such a way that the image of our cubic, our quartic degree genus 3 curve is the singular locus of a unique net of quadrants. So there are 3 quadrants forming the net, and there's another mistake that T1 should be T3, obviously. So you take that net of quadrants and you take the locus of singular points of the singular quadrants, and that is the image. You have one of those for every even theta characteristic of this point cubic curve. Questions or comments? Okay. So now, Bill, I'm gonna shoehorn this in, even though we only have 5 minutes left, because this is what you were talking about. Okay. This is hidden in what we have just said, and I'll show you how. Take any complex number with the property that you take its additive inverse, its multiplicative inverse, and the additive inverse of its multiplicative inverse, and you ask that they be distinct. So that's almost all. You're nodding your head, Robert, did you? Yeah.
It is clearly all.
Okay, and you take its cross ratio, and you get this harmless looking thing that only depends on the square of your complex number. You send C to infinity minus C to 0, C inverse to 1, and the minus C inverse to the cross ratio. And lo and behold, that the elliptic curve that has that as its lattice, okay, the upper half plane period or lower half plane period, wherever it came out, is that omega. Does anybody know what the Greek lattice in the Greek with the twin on in the top? I needed a letter
It's
that
pi. It's a variation of pi.
Star pi.
What is
It's
it?
a variant of pi,
Ah, I see.
even though
What
it
is it?
looks like you make.
I'm impressed. Anyway, lo and behold, we get, and in action, if we had time, which we don't, we would use this to make the bundle whose sections are quarks and leptons out of this computation. Okay, And it turns out that this expression, and for that C plus over C minus blah, is this quotient of theta characteristics. Seems to have nothing to do with anything that we are. But if you define alpha to be that minus that omega plus 1, well, the theta, there are 4 theta functions. One where you add half, one where you add a half to u, and one where you add half to both of those. That web of quadrics in this determinant, that web of quadrics becomes a linear determinantal presentation of our branch curve. That's the alpha, right? So long and short of it, and I'll stop there because I'm out of time. Relationship between alpha and the C, this random C we picked, is that you can get the C squared from the alpha, you can get the alpha from the C squared, and I'll end with this. That those 4 C alphas, C alpha T1 plus T2, C alpha T1 minus T2, and then the other way, the C alpha in front of the T2 instead of the are 4 bitangents of the plane quadratic that are isogenic. That means if you take all 4 of those bitangents, there's a quadratic, a conic that runs through the intersection point. Anyway, that is the difference of the 2 liftings of those bitangents that give you the cohomology that you need to produce quarks and leptons. And I will run, but yeah, you agree as a net. You take the 8 base points of those families of quadrics in P3, that's called the Cayley octad, and you write them down and you project project one of those points, any one of those 8 points, into a P2. Look where the other 7 points have gone. Those are the 7 points that get blown up to make the Delpeccio of degree 2. So for every even theta characteristic, you have a planar presentation. You do this same game, you get all the plane presentations of the Delpeccio of degree 2. I never knew that.
That's faulty.
What's that?
I mean, this is faulty for them.
Oh, this oh, this goes, I think, before both.
Yeah, perhaps, yeah.
Yeah. Okay, so I will stop there because I'm.
Thank you.